All right, so it's around 3 o'clock in the morning right now, and we have a Linux kernel module to write. So the thing is, a lot of times I've noticed people want to get into systems, people want to get into writing operating systems, and they kind of forget about the fundamentals and like the basic things that they need to know, right? And I thought a good way to get into it would probably be to teach people how to get, you know, a kernel module up and running. And the thing about kernel modules is it's basic C, right? So if you know C, you just need to add a little few extra lines of code to actually make it compatible with running as a module, right? And the difference is usually when you're writing C, you're interfacing with stdio, right? Your standard input output. But when you're writing a kernel module, essentially you have to use special functions, right? And that's basically part of the Linux headers. And what those functions are basically ported over functions from the standard input output for the kernel, because you're not interfacing with a terminal or an stdio or any sort of teletype, right? So yeah, I think the first step for anything, writing code in general, I think that would be to look at the docs, right? so so here we have the docs for the Linux kernel. It kind of doesn't matter which version you're looking at, or what kind of where you can find these docs from, because it's pretty standardized at this point, writing a kernel module. So yeah, so I think we should get started. I think the first file that we would need to make is just the module itself. We can try to speedrun this using Neovim. So yeah, let's kind of get started by creating a file. So let's see. All right, so that should be it. You just create a new file. I'm using Neovim right now. You could use any text editor or IDE that you want, preferably Neovim because it's fast and it gets the job done. It's lightweight. I could go on for days about Neovim, but there's that. So yeah, let's kind of get started doing it. Okay, so I think I'm just going to include the default Linux headers. So init.h, and then I'm going to do a that should work. Include Linux. Wait, module. I think that should be valid. And just for safe measure, let's include the schedule.h. Okay, so once that's done, I think to get started on what we're trying to achieve here today, the first thing we should do is kind of figure out, how our kernel module is going to be compiled. And I would like it to have certain parameters, right? So we're going to just draw a process tree from a specific root PID. So for that, let's kind of allow the user to pass a parameter with our kernel module during compilation. So for that, we need to have a int that we can reference later. So let's do static int target PID, and we'll just set the default to PID 1, right? So then it can just basically print the entire tree from the first process, init process. So let's do module param. So this is essentially used to set parameters for the module. So like I mentioned, during compilation, we need to set parameters, right? So we need to let the user pass integers. So what we do here is just set module param and just call our target PID, and then give it an int parameter and set a permission bit so that we can actually allow the module to accept ints, right? We can allow it to accept an integer so that it can be processed later. So once that's done, let's get started on how to print this damn tree. Okay, so what we should be thinking about is basically just a simple ASCII structure. So for that, let's just create a function to print the process tree, right? So here let's have a task struct, which essentially is a struct that keeps track of every single task that's existing in this tree, right? And we can add a depth for the tree so that we can map out our child processes and make a difference between the child and the parent processes, right? So I think we should have a clear distinction. Yeah, I think that should work. Okay, so now that we have this, an important thing to consider is that our kernel doesn't have stdio, like how I mentioned, right? So we're going to have to use a special function to print information to the kernel, essentially. So we don't have the privilege of using stdio to read stuff on the terminal or teletype, right? So what we're going to do is use this specific function called printk, right? So printk is like printf, but it allows us to print to the kernel. So we can do printk and use kern info, right? And this is basically a macro that allows us to print information for the kernel, which can be read from dmessage, right? Dmessage is nothing but a logging daemon, and a daemon is nothing but a software that runs in the background without any user interaction. So what this flag or this macro essentially does for us is it lets us write messages into dmessage, which can be read later on as a log of this specific kernel module or whatever it did in its time of execution, right? So what I'm kind of doing here is just writing out a format for the tree that we have here. Let's add some depth to this tree. Now that that's done, list for each, right? So it's kind of a function that we need to use as part of the kernel headers to iterate and find the processes from our root. So essentially what we've done right here is created this iteration, right, to increase the depth every time we come across a child process in our ASCII tree. I think next what we have to do is kind of create the init and exit processes. So in a kernel module, while writing one at least, the init and exit process is kind of what allows the module to be compiled, and this is what is seen by the kernel as like an entry and exit point for the module. So what we need to do is basically come up with a function for both of these, and then specify using a built-in function from the headers that these two functions that we have written is what we are going to use in this module as our init and exit functions, right? So let's kind of get started on that. So what I'm doing here basically is printing to the kernel, to the dmessage basically, that this is the PID that I'm using as the root, right? And this we have kind of set already using the module params or the default value as 1. What this init function basically does is tells the dmessage daemon that this is the root PID that we're starting with, and we are going to have to also iterate through these processes, right? So let's just do that here. You can break the inner loop here. So this is not a traditional loop, this is part of the headers, so that's why our LSP will shit the bed if it sees this. So I'm just not going to activate the LSP right now and directly just write and quit before the LSP starts screaming at me. So yeah, now I think our final goal would be to write our exit function, and so that would look pretty similar. We can just do static void monitor child exit void and just give a print k saying, again, we got to add the kern info, and yeah, I think that's our most important parts of our kernel module is done, at least the writing code part. Now all that's left is to set the init and exit functions. So module init, that would be our monitor child init function. We don't need to actually call it like that, we just need to set the function. Module exit will be, yeah, that's pretty much it. So before we get done, there's one more thing that we need to do, that is to give the descriptors to our module, right? And that's pretty important because our module will have a tough time compiling without that. So let's just module license, yeah, GPL. Honestly, that's your wish. All of these can be whatever you guys, feel like writing into it. So the description is also something that's very trivial. Kernel mod example. And finally, we can just add the author. Right now, what we can do is our makefile. I think it's pretty straightforward. So I think we can get started with that. Let's kind of give the output name for our makefile. So what was our file name? Create new proc.c, right? So let's just do create new proc.o and then all. So now what we can do is make and then give our flags for making this file, for making this binary. So we can just do lib modules, and what we have to add here is basically our uname, and then we'll add our clean here. I think that's about it. Let's do, yeah, so let's just run make, see what happens. Looks like there is a small error. Oh, my bad. Yeah, this is a simple fix, and I think we can run make now, and what we will see is the entire module being compiled using our makefile. Now the important thing is you can't actually compile this using GCC because some of the function calls that we're making from the header will just be considered as invalid, right? And so what we should be doing is ideally using a makefile to compile a kernel module. So once we've done all that, we should have a whole host of new files here, right? And what we should do now is kind of spawn a new terminal just for convenience, and we can do a sudo int mod, and let's kind of create new proc.k. oh, right? So this is the final step, right? Once you compile, once you do everything, you just got to insert the module into our kernel. That's what insmod does. So let's run that. So just give in your sudo password, and once that's done, what we can do is if no separate terminal, we can just run d message here, and what we can see here is our process tree, right? This is what we formatted, and we can see all our processes and its child processes right here. Tree depths, everything we implemented is right here. So this is essentially what we just wrote. It's been loaded into the kernel as a module, which is why we can see its output in dmessage right here. So if we do a dmessage c using a sudo, that would basically clear everything and print the current dmessage. And now if we just do sudo dmessage, it would be empty. My bad. It would just be empty, right? So there's that. So yeah, I hope this taught you guys a thing or two, and I hope it was helpful, to be honest. It's pretty trivial to write a kernel module, but it is pretty fun because you can kind of figure out the bounds you can go with this, because it's just basic C at the end of the day, right? So with C you can do a lot, especially with Linux, because a lot of its support is written in C. So you can start writing device drivers, you can write a whole bunch of stuff with just basic C and knowing a little bit about the Linux kernel. And also reading the docs, pretty important, gives a lot of information. And experimenting also leads to figuring out new things that may not be written in most of the guides or articles, but maybe hidden somewhere in the docs, right? So yeah, Docs are use case specific, right? But you got to figure out the use case, and for that you got to experiment, which is why I say, just write code, just do the damn thing and you'll figure out stuff. So yeah,